Now that we have identified the cause of the warning message in the previous video, we will demonstrate how the velocity in the pipes can be optimized through the use of one of FluidFlow's special features, the automatic pipe sizing. Our objective is to change the size of the pipe to get a better velocity in the pipes. This feature enables users to identify the most appropriate pipe size based on the sizing model specified by the user. It involves three options for sizing criteria: economic velocity, by velocity, or by pressure gradient. For the two latter options, a figure needs to be provided as a sizing basis for the solver. The by velocity option will make FluidFlow calculate the pipe diameter to get exactly the specified velocity. The by pressure gradient option will make FluidFlow calculate the pipe diameter to get exactly the pressure loss per unit length specified. On the other hand, the economic velocity is solved by the software, using a complex equation involving at least fluid densities, installed costs, power costs, etc., all of which are fully defined by the software with a default value. Users can update these figures as intended and can be accessed on the Database tab under Pipe Sizing Data as shown. We will size the pipes based on the economic velocity, so we leave the sizing model with this option. The pipe size we want to calculate depends on the flow. So to get this result, we need to control the flow first. In the current model, we have not yet made any attempt to control the flow. Once it leaves the inlet boundary, the fluid distribution is governed by its system resistance. Thus, the flow tends to take the least resistance. And when we show the flow through each component user, we can see that in its current state, the flow to a component is imbalanced, and it decreases as it goes further away from the inlet boundary. Hence, we need to implement means to control the flow to each destination component, and the first step in that process is sizing the pipes. Accordingly, to do that, we will change the model. Now, the model we want to build is the one shown in the image. Now, we need to specify the flow instead of the pressure in every outlet boundary. Thus, we will replace all the pressure boundaries with known flow components. By multi-selecting all these nodes, we will update their flow settings simultaneously as 10 cubic meters per hour each. Now, when we hit Calculate, the solver will try to force the specified flow to occur on each of the components. However, in its current state, the model is overconstrained, as we have specified flow throughout the system, but pressure is not specified at any point in the model. As discussed in the previous sessions, at least one pressure node, either as a known pressure or a reservoir component, is needed for the solver as a reference in initiating the calculations. Thus, in the case of our current model, the solver cannot provide a correct result. Hence, it encounters a calculation error. To correct this, let's specify the pressure in the inlet boundary as shown in the image, which is the model we want to build. Notice that the pressure in the inlet boundary is 1.5 atmospheres. To do this, let's replace the inlet boundary with a known pressure component instead of a known flow. Let's set the pressure to the desired value. When we calculate the model, notice that there are new warning messages for additional pipes exceeding the velocity limit or the pipes experiencing pressures below the fluid's vapor pressure. However, notice that the low velocity warning message is gone. When we show the flow to each known flow component, we can see that the software has forced the system conditions to meet the required flow for each. We will set aside these warning messages, as these will be corrected as we move along. For demonstration purposes, we will use economic velocity as our sizing model to determine the appropriate pipe size. This sizing model is the default setting for the pipe material we have applied. Using this information, we will replace the original pipe sizes with another standard size closer to the exact economic size identified. To make the replacement of pipe sizes easier, let's multi-select the pipes and show the economic size result on the flow sheet. After replacing the pipe sizes with the economic size and hitting the Calculate button, we can observe that the velocity warning messages are gone. This can also mean that the pipe sizes for the model are appropriately specified. However, as we replace the pipe sizes, we encounter a warning message on the T-junctions regarding the application of idle-chick-T relationship. Generally, the user may opt to ignore this message or not based on engineering judgment. In this case, the warning messages refer to the possible loss of calculation accuracy in the T-junctions because relationship data has been extrapolated. Still, it is worthwhile checking on the calculated K values to ensure these are within an expected range. You can also cross-check by using another T definition and verify that the calculated K values and pressure losses are similar. This is the case here, and so we can safely ignore the warning. But for demonstration purposes, we will try addressing this warning message by setting the T definition as crane. So when we hit Calculate, there are no more warning messages for the model. After this, we know how to set the flow with the known flow component. We've experienced an example demonstrating the need to specify the pressure in at least one boundary. We observed how to use the results from the auto-size pipe feature to size the pipes and how this cleared the warnings due to high or low velocity. Also, we further discussed the warning messages that appeared during the process. In the following video, we will show how to model controllers to get the desired flow instead of using the known flow boundary.